Bismillahirrahmanirrahim. Assalamu alaikum, dear students. So yesterday we discussed in detail how GFR is determined, how filtration coefficient and net filtration pressure determine the GFR, and how the different pressures which determine the net filtration pressure can be altered in different situations, thus leading to abnormalities of GFR. So there is a very important question which is often asked, that give the determinants of GFR. Please do not forget to mention all of these factors. This is a very important question and you must remember all of these factors. First of all, the most important factor is the glomerular hydrostatic pressure, and it is the pressure of the blood or fluid within the glomerular capillaries, and it is an outward force of around 60 millimeter mercuries, and it depends upon your blood pressure, which is your arterial pressure. It also depends upon your afferent and efferent arteriolar resistances. So it is very obvious that if the afferent arteriole is dilated, more blood is going to come within the glomerulus and more filtration is going to take place. And if your afferent arteriole is constricted, as is seen in sympathetic activation because of epinephrine and norepinephrine, there is going to be reduced blood flow to the glomerulus and the GFR is also going to decrease. Opposite to the afferent arteriole, we have the efferent arteriole. When there is efferent arteriolar constriction, as seen in the activation of renin-angiotensin system, when angiotensin 2 constricts the efferent arteriole, the blood is accumulated within the glomerulus and the GFR is increased. But when there is dilation of your efferent arteriole, there is going to be the passage of the blood from the glomerulus is going to be very quick and the GFR is going to decrease. So you must remember how these three factors determine your glomerular hydrostatic pressure. Next we have the glomerular capillary colloid osmotic pressure, which is because of the plasma proteins which are present within the glomerular capillary. The next factor which determines the GFR is the Bowman's capsule hydrostatic pressure, and it is because of the fluid which is present in the Bowman's capsule, and it is of around a value of 18 millimeter mercury in a normal healthy nephron, but this pressure may be raised in obstructions of the urinary pathway, and raised hydrostatic pressure will oppose the GFR. Then we have the Bowman's colloid osmotic pressure, which is normally 0 because there are no proteins present in the Bowman's capsule. But if there is abnormal presence of proteins within the Bowman's capsule because of leakage of proteins from the glomerulus into the Bowman's capsule in a condition known as minimal change disease, the proteins within the Bowman's capsule are going to attract a lot of water from the glomerulus and aid filtration and increase GFR. Then, as I already mentioned, that the sympathetic nervous system is also involved in determining your GFR. Your sympathetic hormones, such as epinephrine and norepinephrine, they act on your afferent arteriole and constrict it, reducing the blood flow to the glomerulus and decreasing GFR. Some hormones are also responsible for the control of your GFR, and among these are present your angiotensin 2, and angiotensin 2 causes your constriction of efferent arteriole, and efferent arteriolar constriction leads to increased GFR. Then we have autocoids. Autocoids are such substances which are produced by the cells of the kidney, and they act on your afferent and efferent arterioles and cause their constriction or dilation. So macula densa cells, which sense the changes in arterial blood pressure by the concentration of sodium in the distal convoluted tubule, these macular densa cells release autocoids and cause constriction and dilation of efferent arterioles. There are several other feedback control mechanisms which are present within the kidney which can also determine GFR. We will be discussing these feedback controls later in the chapter. So this is a very important slide. You must remember all of these factors, and this is an important question from exam point of view. So it is very important to keep your GFR within a normal range of around 125 mLs per minute or 180 liters per day, because despite changes in the arterial pressure or your blood flow to the kidneys, your urine excretion must be around 1.5 liters per day average. And when your urine volume is less than 300 mLs per day, it is known as oliguria, and which is abnormal condition and harmful for the body. And if the excretion is greater than 3 liters per day, this is known as polyuria or excessive urination. So both of these conditions are harmful, and it is very important to keep the urine excretion within a strict range despite changes in blood pressure, and this is known as autoregulation. So at autoregulation is the maintenance of your GFR within normal values despite changes in arterial pressure. So there are two mechanisms which are involved in your GFR regulation despite your arterial pressure changes. One is renal autoregulation, जिसके अंदर आपका tubuloglomerular feedback mechanism आता है, which involves your JG apparatus, your juxtaglomerular apparatus, the macular densa cells, etc. And the second mechanism is myogenic control. We will be discussing both of these in today's lecture. The second mechanisms which are involved in your GFR regulation are glomerular tubular balance, and it is the adaptive mechanism of your kidney in which the reabsorption of substances is altered when the GFR is increased. So when there is increased GFR, the reabsorption of substances increases. When there is decreased GFR, the reabsorption of substances decreases. This we will discuss in for lectures later on, but today we are going to discuss renal autoregulation, our glomerular feedback, and our myogenic control. So what is meant by autoregulation of GFR? This means that your GFR is kept within a constant range of around 125 mLs per minute despite wide variations in arterial pressure. So this is known as autoregulation of GFR. So why do we need to auto-regulate our GFR? To maintain a relatively constant GFR and to control renal excretion of water and solutes, we cannot allow large quantities of water to be excreted from your body every time your blood pressure increases. This might be very harmful. So, and also we cannot allow your water to accumulate within your body every time your blood pressure decreases. So there are special mechanisms in place which keep your GFR normal despite changes in blood pressure, so that excreta which need to be excreted from the body will be excreted and not stored within your body, and this is very important for normal functioning of the body. तो GFR को strict range में control करना बहुत important है. So first let us discuss the tubuloglomerular feedback mechanism. You are already aware of this mechanism. You have already studied this back in the unit of circulation, but we are going to revise it again. So as the name mentions, the tubuloglomerular feedback, as the name indicates, that tubules send some feedback to the glomerulus. So how this works, let us discuss. It involves your JG complex, juxtaglomerular complex. Juxta means near or close to or present in the vicinity of. So this complex is present near your glomerulus. This is the reason it is known as juxtaglomerular complex. It consists of macula densa cells and your JG cells. Macula densa cells are special thick cells which are present in your distal convoluted tubule, and they sense changes in volume and solute concentrations, especially concentration of sodium. Then we have the JG cells, which are present within the walls of your efferent and efferent arterioles, and they have a very important function. They secrete renin. So let us look at a picture for better understanding. As I mentioned before, that your nephron is so arranged that your efferent and efferent arterioles split into the glomerulus, and around the glomerulus is present your Bowman's capsule, which then divides in forms the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule passes between your efferent and efferent arterioles and then form the collecting ducts, as you can see over here. Here you have the efferent arteriole which divides into the glomerular capillaries, then the efferent arterioles, and as for your nephron, your Bowman's capsule divides into the proximal convoluted tubule, your loop of Henle, and your distal convoluted tubule passes between your efferent and efferent arteriole. Don't be confused. मैंने आपको पहले भी बताया था कि आपकी बुक्स के अंदर जो स्कीमेटिक डायग्राम शो की होती है जिसमें Bowman's capsule, proximal convoluted tubule एंड लूप ऑफ हेनले एंड डिस्टल कन्वोल्यूटेड ट्यूब्यूल इस तरह शो किए होते हैं, उसमें नेफ्रॉन को ओपन करके शो किया होता है, जस्ट फॉर योर बेटर अंडरस्टैंडिंग. इन रियल life or in real situation, the nephron is such folded that the distal convoluted tubule passes between your efferent and efferent arteriole, as you can see in this figure. So here you can see your distal convoluted tubule is passing between your efferent and efferent arteriole. If we zoom this picture and look at what is happening here in this section, you will see that here you have the efferent arteriole which splits into the glomerular capillaries, which then form the efferent arterioles, and here you have the Bowman's capsule. This is the proximal convoluted tubule which forms the loop of Henle, and then there is the distal convoluted tubule which passes between the efferent and efferent arterioles. This distal convoluted tubules has special cells in its walls which are known as macula densa cells. These cells are able to detect sodium concentration, and if the sodium concentration is low, they send signals to the special cells of the efferent arterioles and efferent arterioles, and cause these cells are known as JG cells, and JG cells are responsible for the secretion of renin. So let us see how all of this works. So whenever there is decreased blood pressure, the GFR is also going to be reduced. It is very simple. The blood which is coming to the glomerular capillaries through the efferent arteriole will have decreased hydrostatic pressure, and whenever glomerular capillary hydrostatic pressure is reduced, the GFR is also reduced. So as a result, the filtrate which is being filtered into the Bowman's capsule will be lesser than normal in volume, and also will contain lesser sodium than normal conditions. And since the filtrate is less in volume, its flow rate across the nephron will also be reduced and lesser than normal. अब क्या होगा कि एक तो filtration ही कम हुई सोडियम की, और दूसरा जब सोडियम स्लोली मूव कर रहा होगा फ्रॉम द नेफ्रॉन, फ्रॉम वन एंड ऑफ द नेफ्रॉन टू द अदर एंड, उसकी रीअब्जॉर्प्शन भी इंक्रीज हो जाएगी. वाई इज़ दैट? बिकॉज देर आर प्रेजेंट स्पेशल सोडियम exchangers in the walls of the nephron which reabsorb the nephron from the lumen of the nephron back into the peritubular capillaries. and when the movement of filtrate and sodium is slower, the exchangers will have a greater chance to reabsorb more sodium. So what happens is that the reabsorption of sodium and chloride is increased because of slow flow, and by the time the filtrate reaches the distal convoluted tubule, the concentration of sodium is very low, which is sensed by the macula densa cells. Now macula densa cells are special cells which are present in the distal convoluted tubule, and they are responsible for the detection of sodium within the filtrate. So these cells will immediately detect reduced sodium concentration, and they will decipher this, and they will understand that reduced sodium concentration means reduced blood pressure. So what these macula densa cells are going to do, as I already mentioned, that this distal convoluted tubule is present between the afferent and efferent arterioles. The organization is something like this. Suppose this is your afferent arteriole, this is your glomerulus, and this is your efferent arteriole. Your nephron is so placed that this is your Bowman's capsule, your proximal convoluted tubule, your loop of Henle, and your distal convoluted tubule passes between your afferent and efferent arterioles, and then it forms your collecting duct. So your macula densa cells are present between your afferent and efferent arteriole, and immediately when they detect decreased concentration of sodium, they are going to send signals to your afferent arteriole and cause dilation of your afferent arteriole. ठीक है, तो जो पहला स्टेप होता है by the macula densa cells is they cause a dilation of your afferent arteriole. Secondly, what they do is they stimulate special cells of the afferent and efferent arterioles, and these cells are known as JG cells, and they stimulate these JG cells, and then JG cells release a special hormone or a special protein which is known as renin. Now let's see how this fits into our flow chart. When the blood pressure is decreased, GFR is decreased, the filtrate is very slow as it passes from the nephron. There is increased reabsorption of sodium all the way. By the time this filtrate reaches the distal convoluted tubule, the macula densa cells sense that the concentration of sodium is lower than normal. There are two steps which are taken by the macula densa cell. First of all, they cause dilation of the afferent arteriole, and secondly they cause secretion of renin through the JG cells. This renin circulates within your blood where there is present a special protein called angiotensinogen, which was formed by your liver like all other proteins. Renin acts on angiotensinogen and converts it into angiotensin 1. Angiotensin 1 then travels in your blood and reaches your lungs, and within your lungs is present a special enzyme known as angiotensin converting enzyme or ACE. This enzyme converts angiotensin 1 into angiotensin 2. And this angiotensin 2 is a very potent constrictor of efferent arteriole. What it does is it constricts the efferent arteriole, and when the efferent arteriole is constricted, there is increased glomerular hydrostatic pressure, and your GFR is increased back towards नॉर्मल. ठीक है, ये बात समझ आ रही है. मैंने आपको पहले भी बताया था कि वेन एवर योर efferent arteriole is constricted, there is going to be increased hydrostatic pressure within your glomerulus, and this is going to increase your GFR back towards normal. So this is how, despite the blood pressure falling very low, we can raise our GFR back towards normal, so that body can produce normal GFR and excrete normal ranges of urine and excrete all the waste products from the body despite there being reduced blood pressure. have the same flow chart from your book, and you can see that when the arterial pressure is reduced, the glomerular hydrostatic pressure is reduced, which reduces your GFR. When GFR is reduced, the sodium which is filtered into the nephron is reduced, and the filtrate is very slow while it passes through the nephron, and a lot of sodium is reabsorbed. By the time the filtrate reaches the distal convoluted tubule, the macula densa cells detect there is very low concentration of sodium, and they do two things. One important thing is they constrict the afferent arteriole. They dilate the afferent arteriole, so more blood can enter the glomerular capillaries. And what secondly they do is they cause the activation of renin-angiotensin system, and angiotensin 2 is formed, which constricts the efferent arteriole. Now both of these functions are going to increase GFR. Let me repeat. Your macula densa cells are directly going to dilate your afferent arterioles. By dilating your afferent arteriole, they are going to allow more blood to enter into your glomerular capillaries, and secondly they are going to cause secretion of renin, which is going to form angiotensin 2, and angiotensin 2 is going to constrict your efferent arterioles, so the blood cannot leave the glomerulus easily. Both the dilation of afferent arteriole and constriction of efferent arteriole are going to raise the hydrostatic pressure of glomerular capillaries and increase GFR. So in this way your GFR is going to increase despite your reduced arterial pressure. So another effect is the myogenic effect, through which you can regulate your blood pressure and GFR of the kidney. Myogenic mechanism is a theory which proposes that blood vessels always resist stretching during increased arterial pressure. So suppose this is a renal artery which is entering the kidney, and whenever there is increased blood pressure, there is going to be a stretch of this renal artery vessel wall, and like all smooth muscle cells, this renal artery is going to resist being stretched by the raised blood pressure, and it is going to try to contract. And this is what happens whenever the vessel wall is stretched. It as a reflex movement, it always contracts. Why is that? Because the renal artery vessel wall is made up of smooth muscle cells, and whenever these smooth muscle cells are stretched because of increased blood pressure, there is going to be excess entry of calcium into these cells, because they have special calcium channels on their surface, and whenever these smooth muscle cells are stretched, the calcium channels open up and calcium enters into the cells, and this calcium, when it enters into the smooth muscle cells, it causes contraction. So whenever renal artery is stretched because of high blood pressure, as a response it is going to contract because of entry of calcium within the smooth muscle cells. This is known as myogenic reflex. So myogenic constrictor response in afferent arterioles occurs within seconds in response to sudden increase in blood pressure. Therefore it prevents injury by attenuating transmission of increased arterial pulses to the glomerular capillaries. So let me repeat, there are two ways to control your GFR despite changes in blood pressure. One is tubuloglomerular feedback, जिसमें JG cells और macula densa cells हमने पढ़े हैं, जिसमें renin angiotensin system आता है. Secondly, there is the myogenic autoregulation of renal blood flow and GFR. So whenever there is increased blood flow, the renal artery is going to be stretched, and like a rubber band, whenever a smooth muscle is stretched, it contracts. So why does it contract? Because renal blood vessels are made up of smooth muscle cells, and smooth muscle cells have special calcium channels on their surface. When these smooth muscle cells are stretched, calcium enters these channels and causes contraction of smooth muscle. So whenever the renal artery is stretched, it is going to contract. अब इसका फ़ायदा क्या होगा? We know that increased blood pressure may damage the delicate glomerular capillaries, and it may even increase GFR to such a huge extent that the excretion of urine may increase to values greater than normal. To maintain the renal blood flow and GFR within normal ranges, the myogenic mechanism takes place, and it causes constriction of the blood vessels, so that a lot of blood may not enter into the glomerulus or destroy its membrane or produce greater than normal GFR. So this is myogenic autoregulation of renal blood flow and GFR.